Skyscrapers are marvels of modern engineering, towering over cities and defying gravity with their immense height and weight. But what happens when the ground beneath them shakes violently during an earthquake? How do these colossal structures remain standing while the earth trembles? The answer lies in a combination of advanced engineering, innovative design, and meticulous planning. To understand how skyscrapers withstand earthquakes, we must first delve into the nature of earthquakes themselves. Earthquakes occur when tectonic plates, the massive slabs of rock that make up the Earth's crust, shift and collide. This movement releases energy in the form of seismic waves, which travel through the ground and cause it to shake. The intensity of an earthquake is measured on the Richter scale, which quantifies the energy released. For skyscrapers, the challenge is not just the shaking itself, but also the frequency and duration of the seismic waves. Different types of seismic waves, such as primary P waves, secondary S waves, and surface waves, affect buildings in distinct ways. P waves are compression waves that move quickly through the ground, causing it to expand and contract. S waves are slower but more destructive, moving the ground side to side or up and down. Surface waves, which travel along the Earth's surface, are responsible for the most severe shaking and damage. Skyscrapers must be designed to withstand all these types of waves, which requires a deep understanding of structural dynamics and material science. One of the key principles in designing earthquake-resistant skyscrapers is flexibility. Unlike rigid structures, which can crack or collapse under stress, flexible buildings can absorb and dissipate the energy from seismic waves. This is achieved through the use of materials like steel and reinforced concrete, which have high tensile strength and can bend without breaking. Steel, in particular, is favored for its ability to withstand both compression and tension forces. Reinforced concrete, which combines concrete's compressive strength with steel's tensile strength, is also widely used. The flexibility of these materials allows skyscrapers to sway during an earthquake, much like a tree bending in the wind. This swaying motion helps to dissipate the energy of the seismic waves, reducing the stress on the building structure. However, too much swaying can make the building unsafe for occupants, so engineers must strike a delicate balance between flexibility and stability. To achieve this, skyscrapers are often equipped with damping systems, which act like shock absorbers in a car. These systems absorb and dissipate the energy from seismic waves, reducing the building's movement. One common type of damping system is the tuned mass damper, a massive weight suspended near the top of the building. When the building sways, the damper moves in the opposite direction, counteracting the motion and stabilizing the structure. Another innovative solution is the use of base isolators, which are installed between the building's foundation and the ground. These isolators act like cushions, allowing the building to move independently of the ground during an earthquake. By decoupling the building from the shaking ground, base isolators significantly reduce the forces acting on the structure. In addition to flexibility and damping systems, the shape and design of a skyscraper play a crucial role in its ability to withstand earthquakes. Symmetrical buildings with uniform mass distribution are generally more stable during seismic events. Irregular shapes or uneven weight distribution can create stress concentrations, making the building more vulnerable to damage. Engineers also pay close attention to the building's height-to-width ratio, as taller and narrower buildings are more susceptible to swaying. To counteract this, skyscrapers are often designed with a strong central core, which provides additional stability. This core, typically made of reinforced concrete, acts as the backbone of the building, supporting the weight and resisting lateral forces. Another important consideration is the building's foundation. Skyscrapers are anchored deep into the ground, often reaching bedrock, to ensure stability. The foundation must be strong enough to withstand both the weight of the building and the forces generated by an earthquake. In some cases, engineers use piles long, slender columns driven deep into the ground to provide additional support. The soil conditions at the building site are also carefully analyzed, as soft or loose soil can amplify seismic waves, increasing the risk of damage. To mitigate this, engineers may use techniques like soil stabilization or deep foundation systems to improve the ground's load-bearing capacity. Another critical aspect of earthquake-resistant design is redundancy. This means that the building's structure has multiple load paths, so if one component fails, others can take over the load. Redundancy is achieved through the use of interconnected beams, columns, and braces, which distribute the forces evenly throughout the structure. This ensures that no single element is overloaded, reducing the risk of catastrophic failure. In addition to structural redundancy, modern skyscrapers are equipped with advanced monitoring systems that provide real-time data on the building's condition. These systems use sensors to measure factors like vibration, tilt, and stress, allowing engineers to detect potential issues before they become critical. In the event of an earthquake, this data can be used to assess the building's safety and guide emergency response efforts. The construction process itself is also a key factor in ensuring a skyscraper's resilience. High-quality materials and precise workmanship are essential to creating a structure that can withstand the forces of an earthquake. Engineers and architects work closely with construction teams to ensure that every component is installed correctly and meets the required standards. Regular inspections and testing are conducted throughout the construction process to identify and address any potential weaknesses. Once the building is completed, it undergoes rigorous testing to verify its performance under simulated earthquake conditions. This may involve shaking the building on a large platform or using computer models to predict its behavior during a seismic event. Only after passing these tests is the building deemed safe for occupancy. It's also worth noting that building codes and regulations play a vital role in ensuring the safety of skyscrapers in earthquake-prone areas. These codes, which vary by region, set minimum standards for design, materials, and construction practices. In countries like Japan and the United States, where earthquakes are common, building codes are particularly stringent. Engineers must adhere to these codes and often go beyond them to ensure the highest level of safety. In addition to government regulations, organizations like the International Code Council (ICC) and the American Society of Civil Engineers (AC) provide guidelines and best practices for earthquake-resistant design. These standards are continually updated based on the latest research and technological advancements, ensuring that skyscrapers are built to withstand even the most severe earthquakes. One of the most fascinating aspects of earthquake-resistant design is the use of cutting-edge technology. Advances in materials science, computer modeling, and construction techniques have revolutionized the way skyscrapers are built. For example, shape memory alloys SMAs are a new class of materials that can return to their original shape after being deformed. These alloys are being used in seismic dampers and other components to improve a building's resilience. Similarly, fiber-reinforced polymers FRPs are lightweight, high-strength materials that can be used to reinforce concrete and steel structures. Computer modeling and simulation have also become indispensable tools for engineers. Using sophisticated software, they can create detailed models of a building and simulate its response to various seismic scenarios. This allows them to identify potential weaknesses and optimize the design before construction begins. In some cases, engineers use 3D printing to create scale models of skyscrapers and test their performance in a controlled environment. These technological advancements have significantly improved the safety and reliability of modern skyscrapers. Despite all these measures, no building is completely immune to the forces of nature. The goal of earthquake-resistant design is not to eliminate all damage, but to ensure that the building remains standing and protects its occupants. Even in the most severe earthquakes, a well-designed skyscraper should be able to withstand the shaking and allow people to evacuate safely. This is why emergency preparedness is also a critical aspect of building design. Skyscrapers are equipped with features like fire suppression systems, emergency lighting, and evacuation routes to ensure the safety of occupants during a disaster. Regular drills and training programs help familiarize people with these procedures, reducing the risk of panic and injury. If you found this exploration of earthquake-resistant skyscrapers fascinating, don't forget to subscribe for more deep dives into the science and engineering behind the world's most incredible structures. Thanks for watching. and we'll see you in the next video.